In this other picture, we see an action out of plane failure that sometimes the forces from the roof will move the wall out of its plane, and we get this kind of behavior. So the study region we are considering in this study is located in Bogota. Specifically, we have here located Colombia in the map. As you can see, we have some activity, earthquake activity. We have subduction on the Pacific area. We have also some faulting that is in the mountains of the Andes. Here I'm showing a plan of Bogota. This is a plan view of Bogota, and this part here are the mountains. This is a model we built with a PhD student, which has a lot of thousands of finite elements. So we were able to propagate an earthquake that happens by the mountains, and it will arrive to the city. The city is in a flat area that is mainly have a lot of deposits of soil, very soft soil. So we see that the actions and state within the deposit, although at the mountains we don't see much activity afterwards. So this is a view of the city, and in the part near the mountains we have this town, which is mainly built with earth, adobe and ramp earth mainly. So here you see how it looks like. So we did a study of this historical center, found that here you can see with the colors, one-story buildings in blue, and in green, two-story buildings. So there are a lot of two-story buildings in this town, and also the one-story all these properties are made of earth. So here we see the thickness of the walls. The thickness varies around, I would say, 0.60 meters, 60 centimeters for one-story buildings, and for two stories, so a little more for the first story walls. We did models of all these houses, and we have those in Revit. So with that, we have a good cover of the architecture features that are present in these houses. Afterwards, we have conducted research on this behavior of these houses, and also some measures for retrofitting. So all these studies have been published already. So I'm showing here some of the papers that we have published in the time. This document is very important because it's the regulation we wrote based on the results of these studies. And you see here some more recent research on this topic. These are 2023 papers, the last ones. So first, we studied the material properties. We have conducted so many tests on this material for the adobe itself, compression flexure, for compression wallets, for ram earth, taking some blocks and getting the mechanical properties for compression, diagonal tension, for adobe and ram earth. All these tests have been conducted for many of the research projects that we have conducted in the time. The retrofitted techniques that we were evaluating at the beginning were very low cost techniques, like installing these meshes. This is a technique developed mainly in Peru. They use a very low cost mesh and attach it with some caps to the wall. Very simple way to retrofit the walls. Also, we have been working with other meshes, with high cost meshes, metallic or some other plastic or synthetic meshes that are attached to the wall through a ball that is passing through the thickness of the wall. We also have tried timber elements. The timber elements have a process to install it in which you need to carve the wall. This is not very good for the wall because we reduce the thickness a little bit, but we need to do this because we don't want the elements to be shown from the outside. So we would like to cover that. So that's why we need to do something like this. And we install throughout bolts to connect both sides of the timber elements. And recently we have also worked on steel plates. The problems with the timber elements are mainly related with the durability, especially because of the humidity that these walls will have during the whole time that they exist. Also, we would like to have something with better strength. One argument to don't using steel plates was mainly related with the incompatibility between the earth material and the steel. And that's something that is very clear when you use very thick or stiff steel elements. But when you don't use that, but only a plate, you will see a lot of compatibility between the two materials. Also, these are connected through the wall. The experimental testing was conducted at Universidad de los Andes. This is our lab. We have a shaking table, reaction wall. Also, recently we have been working with Pontificia Universidad Javeriana. Especially, I have a PhD student who works for that university. So we have been doing testing also at that university. So initially we do this kind of testing in which we apply horizontal load to measure the in-plane capacity of the walls. We see in Adobe a lot of cracks, while when you go to, for example, ramp you see only some cracks that it will show up, and then you get, for example, in this case, this big part of the wall will get unstable eventually. So that's the way that these big blocks of ramp earth will eventually collapse. So then we have been doing in-plane testing for one-story walls with openings. So to simulate the front of the houses, you see the doors and the windows. So we take this kind of geometry to the lab, install it there, and apply loads horizontally to see the capacity. In this case, we also retrofit some of these with, for example, timber elements like you can see here. So the main advantage of this system is that you see that the cracks will not be able to propagate extensively. They will appear, but they will be controlled by these timber elements that we have installed. We see here the big differences in behavior between the two cases, between the cases without retrofitting. The original one is this one, and then retrofitted, you see a lot of increase, especially in the deformation capacity of the wall, and also some increase in the strength. But the most important one is in the deformation capacity. Also for Adobe walls, you see here hysteresis cycles that are fatter, and also they will go to larger deformation displacements. In this case, you can see the profile of displacements along the wall. So you see that there is a concentration of displacement in this position. So when you have this opening, you will concentrate the damage mainly on these piers. So that's something that called our attention in terms of the retrofitting technique, that we should include elements there. We also have conducted tests on this kind of modules with windows and doors, in which you can see here that the cracks are not, they appear, but they are controlled by the timber elements. Here also we have doing testing for piers, because we observe that this pier is very critical in its behavior. As you can see, the pier will have the typical X pattern cracking that is present in masonry structures. So here you see this and this. These are those two specimens, similar failure modes. However, when we tested out of plane, we didn't see any damage, and we were very surprised because we were thinking that there will be start damaging at the same time that these other two specimens. But then suddenly the specimen collapses. So that we observed was that inside the wall, we didn't see the damage, but it was all the material inside, it was highly damaged. So eventually it lost the vertical capacity. So we try to retrofit this kind of walls. In this case, we put need to change the sorry, I will put this back. In this this is without the retrofitting, and here we put some plates, and you see how these plates will prevent these large cracks to appear. So we have damage in the lower part of the specimen, but in general, the capacity, the deformation capacity is much higher than the other wall. Also, we have done some kind of beams. These are actually out of plane walls that we install horizontally to see the behavior, out of plane behavior. Without reinforcements like the wall here, we need to reduce the span of the specimen, so we are able to actually see the failure, because otherwise with the self-weight, it will fail without any additional weight. So in this case, we put these elements to support the specimen before the test, and then we remove it and apply some little load, and you will see that the element will collapse immediately. In the specimen down here, we put at the bottom and at the top, we put some steel plates and connect those plates with bolts between them. So you see the behavior in this case is more similar to reinforced concrete, in which you see a cracking pattern. Some cracks appear and they are controlled by the reinforcement. So the specimen will have a much larger strength, and also the most important, the formation capacity. So this was apparently a very simple test, but it was not, because we need to build this like opposite and then rotate at the lab. It was not very simple test actually. With this, we did some testing, a lot of this. We were able to build a curve that will allow us to estimate or to get an equation to predict the flexural capacity of an earthen wall with these plates included. This equation was verified experimentally and also analytically, so it works very well. Also, we did some out-of-plane testing using very simplistic way. Take the wall completely and then put it in an angle, and with the angle, try to measure the out-of-plane acceleration that we may have. So these are the results. This Adobe wall at the top is collapsed, have collapsed after just rotating a little bit the framework that we have for the test. Here we put some timber elements, and as you observe, the timber elements will control the collapse, out-of-plane collapse of this Adobe wall. We also did some testing for the connection. We would like to know what is the behavior of the connection and the compatibility between the two materials, considering the ball that is passing the wall. So we did this test to get some properties for our analytical model that we did for the flexural behavior that we have before. We needed to have some kind of the interaction between the material and the earth So we conducted this test to do that. Okay. Later, we start thinking that we should do the same testing for two-story structure, because as you saw in Bogota, we have so many two-story structures that we have tested only one story. So then we came out with this specimen. This is a PhD student here, Daniel Ruiz. He is from La Pontificia Universidad Javeriana. So we did the testing over there. And at the top are two students that participated in the project. They are master students. And the guy here at the door is the one who built this wall. He's a very well-known person that knows all these techniques from the past and is able to build this kind of houses using the very old techniques. So here is how the wall behave. Here we have some cracking as we expected here at the pier on the second floor. At the first floor, we didn't get much damage. We then installed some retrofitting for the wall and then tested again. And here is the behavior. So with the retrofitting element, you see how the wall will have a very large deformation capacity. You see the very large displacement that we are applying with the two actuators along the wall. So very good behavior, high capacity, deformation capacity, and also some increase in strength. As I mentioned before, the increase in strength is not as high as the increase in deformation capacity. So here you can see the text. Sorry. Here you can see the hysteresis loop similar to the one we just showed before. We also did some checking table testing. Initially, small scale, very sorry. So here we are applying an earthquake, and we see the collapse pattern of this kind of houses. This is a small scale specimen. We have put some timber elements to see the improvement in the behavior. So in general, we got very good result. We also test this for two stories, small scale. But these tests are interesting, but not very good to get information out of them. So then we decided to go to full scale specimens. So we will have seen, this is a picture for an earthquake, that the corner is a very critical point for the out of plane actions in this kind of houses. So we would like to have in the lab one of these corners. So we build these specimens. Here we were able to put on the checking table 3 specimens at the same time with different techniques. The first one here, it doesn't have anything. It's adobe wall. The adobe for this and for the previous elements that we have built in the lab were obtained from places that were under demolition. So the adobe are preserved for maybe 50, 100 years or more than that. So you see here the damage in the perpendicular wall and also in the wall that is on the out of plane actions. And one interesting thing that we see here is that the walls that are retrofitted didn't suffer any damage while this was collapsing. So this is was a very good evidence the advantages of the retrofitting techniques. Here the other wall is already just, it doesn't exist anymore, and these walls too, these two here are with some very little damage, very stable. Also, we did testing for rammed earth structure. Other techniques are included here. For example, this one includes steel plates. You see the big cracking cracks that appear through the wall, the very extensive damage that is suffered by the wall. We see here collapse already. As you can see in this other video, this support of the block here is almost you know, you see this block here is not supported under the below block. So this is the way we observed in many of the experiments, that this will get unstable eventually and it will collapse completely. We also tested this with the meshes. These are the meshes that we tested, the very good quality, high cost meshes. However, as you can see in this experiment, the flexibility of the walls are very high. And at the end of the experiment, the walls will have a very high permanent displacements. So this is an interesting technique that will allow people to get out of the houses, but probably the houses will be demolished after the earthquake because of the very high permanent displacement that will remain in the walls. Some simulations also have been conducted in many different software, like OpenSys, or even we have done this with Abacus. As you can see here, this wall is collapsing here out of plane, and this retrofitting specimen at the bottom, it doesn't have collapse, and the walls are very well, behave very well in this case. Finally, we have done testing of two-story specimens subjected to two components of ground motion, as you can see here. So here we see a specimen in the left without any reinforcement, and at the right with reinforcement, we see the collapse of this specimen here, and this one here is with some damage, but it behaves very well, very stable, no permanent displacements that are important. Here is how at the end it was, we got complete collapse of this specimen without reinforcement. Finally, I would like to show some applications. The first application that I would like to show is this document, the AIS 610. This document was prepared by some people in Colombia. I was part of that group. I was actually leading this part of retrofitting, and we have included some of the results of all this research in this document. And this document is now a standard for the seismic retrofit of historic buildings made of earth. We would like to have this kind of initiatives also for other materials. We are now working with the Ministry of Culture in masonry, conventional masonry structures that are very old. This document award the 2020 Teodoro Sanchez Award from the Colombian Society of Engineers. And also these techniques are now implemented in some cases. Here, for example, they are also retrofitting the diaphragm, very important for connecting the walls between them and be able to take advantage of the redistribution of the forces when you have an earthquake. So that's all that I had. Thank you so much for your attention. I don't know if there are any.
Thank you very much, Juan Carlos, for an excellent presentation. I'm sure that's very stimulating, actually, and it's very nice to see how the all the research has then fed into actual applications, and how the research has been refined from using both experimental and analytical approaches. Are there questions from the audience, please? Feel free to switch on your camera and open your mic, or if you want to write in the chat. I have a first question, while maybe others are thinking about it. So in the very early examples you presented, case of this bracing or confinement, because it's almost equate to the confinement that one would apply in a confined masonry, traditional confined masonry structure, with timber plate. If you're using this as a retrofit, how do you create the recess in the Adobe to put the timber plate at the same surface level as you were showing in those pictures?
So we need to initially carve over the wall. This wall has mainly 60 centimeters thick. So we need to carve a little bit to be able to enter the elements some amount. So then we can put some covering so the elements are not visible because in these kind of structures, they mainly want to have the same appearance. Actually, at the restaurant of our university, you probably go in there, Dina, when you come here. We implemented this technique, but in some parts we discover and the elements, the retrofitting elements, so you can see then how they are connected and supported. So that's something that we need to do ahead. Is this carving the wall a little bit? So that's why this technique of these elements, we found it a little bit invasive because, sorry.
Long talk.
Yeah, we need to take some material out of the wall. So although it works very well in the lab, we actually would like to have other techniques like the steel plates that are very
thin.
Yeah, very thin, and then we don't need to
And how do you connect them through the thickness?
We first drill a hole and we put a bolt to connect the two elements in both sides of the wall. With the timber elements, we need to pull the bolts with nuts at the end, so they will also take some space, those nuts.
Of course.
With the steel, we welded the element to the plates, so we didn't need the additional space for the nuts.
Thank you for providing these details. And there is a question from Arturo Martinez. How are those vertical retrofit elements connected to the foundations?
Yeah, that's a very important question and very interesting and very nice that you have asked that. We have two ideas. One idea is that you have these horizontal rings that will go around the construction. So if the walls are not very long, these horizontal rings will be able to support the out-of-plane actions. So we don't need a strong connection to the foundation. But if the wall is very long, then the rings are not enough to support the out-of-plane action. So you need to put some, the vertical elements need to be anchored to the foundation. So locally, we need to do some small elements at the foundation, but we didn't put like beams out of, in all the walls of the construction, because that is we have in the past we did that in some projects, but it is very we like damage the whole construction and the details and everything. So for now, that we are doing is making some foundation very local for those very long walls to be able to anchorage the vertical elements. And we think that the rings horizontally will help, so the actions are not that concentrated on those vertical elements.
Thank you very much, Juan Carlos. And I don't know if there are other questions. from the one final question for me is how do you think that extends to other type of masonry structures? We will see in a little while that, for instance, in Nepal, they have developed a very similar layout of horizontal and vertical elements that usually they are installed in shotcrete, so with reinforcement for brickwork, and in some cases also for stonework. And I think, of course, the concept is the same, but the difference is fundamentally in the relative stiffnesses of the materials.
Yeah, these techniques, in general, as you know, the strength of the original material is very important, the strength and the stiffness of the original material. So for this case, for the adobe and the ramp earth, we consider that we have the weakest possible masonry system.
Yes.
So for that case, I think we need to put more elements and invest a lot of more money because the material itself is very weak. In other cases, for conventional masonry that is not adobe or ramp earth, I see other techniques maybe more appealing, or maybe use, or no, we don't need so many elements as you saw in this case. For example, one thing that I didn't mention, but we did in the lab, was why not we put inside the wall some elements? We drill a hole inside the wall and put some, let's say, some bars, steel bars, and then try to compress the wall. That looks like something interesting, because in masonry, in conventional masonry, that's something typical. We drill a hole inside, and then we put some elements for retrofitting.
Yes, to improve the bending strength with some pre-compression. Yes,
exactly, like doing this reinforced masonry, right?
Yeah.
Kind of. But for this material, we did put it in the checking table, and actually it failed before the other walls. They didn't have any retrofitting because the material is very weak and actually damage the wall even more.
You initiate Poisson ratio in the other direction, so yes,
exactly.
It clearly doesn't quite work. Yes, indeed, there are in the Nepalese code there are some recommendations to introduce this vertical reinforcement at corners, but of course it's easier to do during construction than as a retrofitting measure, because as a retrofitting measure the drilling becomes very complicated. Thank you again very much. We love to hear from other colleagues that are online, so please keep either switch your microphone on or type your questions in the chat. And meanwhile, Juan Carlos, thank you very much again for the very interesting presentations and lecture. And I will pass the words to Rohit Adhikari that will talk about strengthening and retrofitting of masonry structures. Thank you again, Juan Carlos.
Thank you so much.
Thank you very much, Dina, and thank you, Juan Carlos, for a very interesting presentation on the experimental tests on retrofitting of Adobe. You will see in my presentation, let me see my slides. You will see many shared concepts and techniques in my presentations. Because the deficiencies we saw yesterday on the masonry buildings, unreinforced masonry buildings in general, are very similar throughout different masonry fabrics. Can you see the screen?
Yes, we can. Thank you.
Thank you. So based on the deficiencies we identified yesterday, looking at different history of different earthquakes, the damage to masonry buildings, we will today see some of the most commonly used techniques to strengthen masonry buildings. So this is the content. We will briefly look at the deficiencies we identified yesterday, and we will talk about some of the most common retrofitting techniques. Then I will show 2 examples of strengthening with detailed analytical and numerical assessment before and after retrofitting, and we will present some key points around retrofitting of masonry structures. So the deficiencies we saw yesterday are at 3 levels: wall level deficiencies, as you can see, and then at cross wall level deficiencies, and the global deficiencies. And we will see the strengthening targeted for each of these 3 levels of deficiencies in masonry buildings. At wall level deficiencies, we have the poor integrity, poor material quality within the walls, poor connections within the leaves, and so on. So one of the retrofitting at wall level is to put through elements. For example, here they have made some holes through the masonry and put a reinforcement bar, and then with some concreting there. So this is there was discussion just before in Juan Carlos' presentations. This is quite destructive and needs careful attention when drilling those holes through the masonry, so as not to disturb or vibrate and lose the bonding of the elements in the wall. And similar to this, there are transversal anchorage through elements, again, made of steel only, and they are locked from the 2 sides, as you can see in these examples. And these have been used in both stone and brick masonry. Again, at wall level, so if the material, especially the binder, the mortar, if it is of poor quality or it has been lost or disintegrated after a long time, then this grout injection can be used to regain the bonding in the masonry. So in this process as well, they create small holes and then inject the grout through the masonry. Another technique here is to use the ferrous cement. So there is a layer of reinforcement on the wall. So usually, in Nepalese practice, they put the jackets on both sides, and then they connect it through the thickness of the wall at a continuous level. Now at cross wall level, when we need a proper connection between 2 walls, this is one of the techniques where there is a strong back holding constructed right at the corner. It can be best placed inside, and with a new foundation for it, not a big deep foundation, but at least to support it vertically. And this strong back is connected by dowels on the both side walls, as you can see. So get the pointer. For example, here this connects this wall, and this dowel here, this connects the other wall. So, and it serves 2 purposes here. So for the low strength masonry, the vertical column imparts some lateral strength, and it also imparts the good cross-wall connection. Again, at cross-wall connection, we can use the same ferrous cement, the RC wall jacketing technique at the cross-wall, so it binds all the walls there together. And this is also again on the both sides of the wall and interconnected through the masonry at certain intervals. As Juan Carlos was showing on the Adobe, so these are some of the practice we can see from different parts of the world. So in Adobe, we have quite large thickness, 500, 600 millimeters. So we have space there to carve the place for putting those connectors, either timber or steel connectors, as you can see in the photographs. So these are traditionally practiced, maybe mostly without any engineering analysis or calculations there. In terms of global strengthening, so these are low-cost practices, as you can see, PP bands, and so on Adobe buildings. So PP bands, mesh all over the wall faces, and then plastering, also using the mud. And on your right, you can see some bamboo vertical elements, and they are used to support the rope joints, so that the rope binds all the walls together. In low strength, the Adobe or rammed earth structures here, this vertical bamboo posts also to some extent impart lateral resistance. And here is again the ferrocement overlay, the RC jacketing, and now in this case this has been applied throughout the walls, all the walls. And these vertical reinforcement bars, these also have a small foundation dog at the base, so that they are vertically supported, and they are again connected through the wall on the both sides, and then finally plastered. So this has been practiced on hundreds of buildings in Nepal since 2009. And during 2015 earthquake, most of these retrofitted buildings stood without any damage, while nearby reinforced concrete buildings were collapsed. So this is complete RC jacketing. While here there is an effort to save the cost and material here, as you can see. This is low density RC jacketing, where we have strips of the RC jackets, splint and bandages. These look very similar to the confined masonry, but these are only on the outer surface of the walls, and of course again on the both sides. So they are connected through the masonry. Again, on the global strengthening side, so the horizontal bands, the seismic ties or belts, as known in some regions. So these are also very effective in binding all the walls together and imparting ductility to the structure. While these are being horizontal structures, they do not really contribute to any vertical lateral strength. So this is quite hard to install these bands. So in new constructions, these are very easy to incorporate, but in retrofitting, so for example, in this first case here, we need to first remove the existing roof structure and then install these roof bands, and again reinstall the roof structure. But in older buildings, this also provides a chance to retrofit or strengthen, upgrade your roof structure itself. So it's a good thing. And not complete bands, but we can use seismic belts. So binding all the walls together at the outer surface can also provide global box-like behavior and impart some ductility. In terms of roof strengthening, so this is not very structural, but this is also horizontal structures, which helps distributing the seismic forces at the horizontal level. So, for example, in this first photo here, the roof structure is without bracing, so we can install bracing to stiffen the roof structure, so we have more rigidity in its plane, and we can also improve the connection between the roof elements within the roof elements. For example, using this metal nails or straps. This is in steel building, a steel roof structure, where you can again using the diagonal X bracing, and this is in timber structure. So we can install diagonal braces and also strengthen the connections within the elements so that we stiffen the roof structure. About the roof and wall connections, so these are walls, vertical walls, and the roof elements are resting on this wall. So in many cases, we have poor connections here, only resting over the wall. So we can improve those by using these straps, nails. We can dig holes and then put nails. But this requires skilled manpower as well as right tools for these strengthening works. About floor strengthening, so the horizontal floors in masonry buildings. So usually, traditionally, they are timber joist supported and topped by mortar floor. So we can improve that by using these diagonal braces in the horizontal plane. We can also put some plywood panels and nail those down to the joists, or we can use concrete overlay, reinforced concrete slab on top of the existing timber, so that we stiffen the floor to better distribute the horizontal action to the lateral load supporting elements. On the same roof floor strengthening side, so for example, this floor is moored topped timber joisted floor, and here you can see this is retrofitting. You can see there are slab strips installed at certain intervals, and they are connected well to the ring beam and to the vertical strong backs. So we stiffen and improve the connection of the floor with the walls. Now we have seen some of the most commonly used techniques to strengthen walls, cross-wall connections, and the global building. Now we will see two examples supported by numerical analysis, and we will see in terms of vulnerability and fragility functions how we can improve the seismic behavior by strengthening. So the first case is a single-storied school building. So this is brick masonry building from Nepal. As you can see here, you can identify several deficiencies here. One most important deficiency is it lacks the seismic bands. So that is very important for the global box-like response. It also lacks the proper diaphragm action. So these are some of the characteristics of the building. This is a school building. The thickness is 250, English bond, so good bond pattern. No strengthening since its construction, and we don't see any horizontal bands. The requirement for retrofit design is that the building should be within the life safety performance limit. Now, the moderate, because this is a school building, we impose tighter safety regulation for schools because of high importance factor. So we aim to ensure that the building should meet the immediate occupancy or moderate damage level after strengthening. And this is in accordance to the Nepalese Seismic Design Code, NBC 105/2020. In Nepal, we have the code defines the seismic hazard to be 0.2G to 0.4G range. So those are the criteria for the retrofit design. So the retrofitting design, as I have put here, should be safe as per the immediate occupancy requirements of the code. So for retrofitting, as seen in the presentation presented by Dina yesterday, she showed the comprehensive strategies for retrofitting. So for the given building, we need to assess both qualitatively and quantitatively how much capacity or what are the failure mechanisms in the buildings are. So before retrofitting in the given existing building, we looked at how the building behaves during lateral action. So in both directions, as you can see here, the outer plane walls, the walls acting in outer plane direction, they are most vulnerable and they tend to separate out from the rest of the building. So the outer plane vulnerability here is the most critical, and that is due to the lack of box-like behavior, which basically is due to the lack of the horizontal bands. And moreover, if we see the capacity curves here for clarity, I have plotted capacity curves of these outer plane walls separately and of the in-plan system separately. In-plan system, the capacity, the base shear coefficient is about 0.4, which is which can be compared to 0.4G PGA, while for the outer plan walls, the capacity is only about 0.2G, which is very low. So we have seen from the failure mechanism and capacity curves, the problem is the lack of box-like behavior and the high vulnerability of the outer plan walls. So again, in terms of fragility and vulnerability functions, for the given hazard of 0.2G to 0.4G, you can see the mean damage ratio, the loss ratio is more than 25% to up to 50%. So 25 to 50% loss ratio, that is unacceptable for this school building. So for the retrofit design, because we have to improve the box-like response, we decided to install a ring beam at the roof level, which helps binding all the walls together. For this retrofit task, it is quite invasive because we need to remove the complete roof, and we need to rebuild it after this ring beam installation. And there is a problem of connecting the ring beam to the walls. So we can use nails or straps at regular interval for this, because if we had reinforcements coming vertically, then it would be much easier to connect this with the vertical structure. But there are none in this building being unreinforced. So we need to use at regular interval nails or straps so that we get proper connectivity between the horizontal and vertical structure. So after retrofitting, if you now look at the failure mechanism, in the original structure, as we saw already, the out of plan vulnerability is the most critical one. But as soon as you install this ring beam here, then the failure mode switches into in-plan failure modes. For example, the shear failure here and the flexural failure here. And whole building acts as a single unit, single box, so that we can see a proper box-like response here. And if we compare the capacity curves here, the in-plan capacity is not significantly affected because we have not installed any vertical elements. However, for the outer plan wall, the outer plan capacity was 0.2G before retrofitting, and it has now come up to 0.4G after retrofitting, which is significant improvement. In terms of vulnerability function comparison for the original and retrofitted building, so we have the hazard range of 0.2 to 0.4G. So you can see in this range, the original building, it had this much loss ratio. Mean damage ratio was up to 0.5% or 50%. But as soon as you retrofit this building with this technique, then your loss ratio is in the range of 0.6 to 0.7 to almost 0.15 or 14-15%. So we have managed to reduce the loss for the given seismic hazard by 14% to 14% only. So this is how we justify the retrofit design with detailed vulnerability assessment. So this building now performs well within the given performance requirement from the code. The second case is a multi-storied rubble stone masonry. So this is 2-storied plus an attic floor here. The floor is mud-topped timber floor. This is again the same hazard because this is also from Nepal. In terms of deficiencies, we can readily identify the poor quality of material, poor quality of mud, and mud is already lost here. Poor wall integrity, therefore, the poor cross-wall connections. Although we can see some larger stones here, but still we need to improve the cross-wall connections. No rigid diaphragm action, although these floors provide some level, but not fully, to the rigid diaphragm action. There is no box-like behavior because we don't see any ring beams there. And the gables are heavy and highly vulnerable. So these are the deficiencies, and we need to, and I want to briefly talk about this building type. So this building type is the most common building type in the mountainous regions in Nepal because of the local availability of the material. And in the last earthquake, 2015 earthquake, these buildings suffered the very high damage. Most buildings collapsed and under significant damage state. So these rates are all damage grade 5, which is collapse. So this is one of the retrofit examples that was implemented by Build Change, and they have retrofitted over 200 of such houses in the period of 2016 to 2020. So about the retrofit elements here, the design includes the RC through elements to improve the wall level integrity. As you can see here, the design includes the vertically strong backs, reinforced concrete columns, which are strong backs at the its corners and at some certain intervals. Okay, and there are RC ring beams installed, and there are RC slab strips installed and connected to these ring beams as well as to these vertical columns. So as you can see, we have implemented the 3 levels of retrofit design. So at wall level, at cross wall level, and at global level. So with these all retrofit elements, and also, sorry, the heavy gable, masonry gable is now also replaced, okay, with light structures such as CGI sheeting. So if you compare the crack patterns, failure mechanisms of these 2 buildings, the existing and retrofitted buildings, in the existing building is, as you can see, there is a complete diagonal crack developed throughout the wall length, okay? And also, so this is in-plane crack. And in terms of outer plane crack, there is complete wall separation here and here, as you can see. So, and the seismic loading in this transversal direction, okay? Now, in the retrofitted case, those cracks are broken, as you can see, as you also saw in the presentation by Juan Carlos. So these elements, these 2 elements have, and also the ring beams installed, they have acted as a barrier for the complete full length crack development. So we have more time for the more deformation capacity, let's say, before collapse. So and also this complete vertical separation of the outer plane walls is also restricted. That is because of those ring beams and the of course the improved cross wall connections provided by the strong back. Here we have considered three different material qualities because those buildings have been built since 80 years, or they might be 80 years old, 50 years old, or 30 years old. So depending on that, we can assume different material qualities depending on the building age. So we considered 3 different material qualities, and this red all are belonging to the original building, and the black colored ones are belonging to the retrofitted building. For now, let's look at the average material quality. So for the average material quality, the lateral capacity was only about 0.08 G for the existing building, while for the retrofitted building, it has improved up to nearly 0.2 G. So we have improved the lateral capacity by more than double. So in terms of fragility functions comparison, so we have the seismic hazard 0.2 to 0.4 G, and these are the fragility functions for the existing building, and these are the fragility functions for the retrofitted building. Again, let's focus on these bold lines, continuous lines, because that is the average quality index building. So our aim, this is a residential building, so the code requires us to meet at least life safety performance level. So for life safety, so this violet is the color for the life safety. For the existing building, for the entire range of PG, the seismic hazard for 0.2 to 0.4, you can see this is reaching 100% probability. So we are 100% sure that this building will perform beyond life safety limit. So this is completely unsafe structure. And again, for the average quality, let's look at the continuous lines. For the life safety performance level, you can see here the probability of the building being in the life safety limit is ranging from let's say 0.5% to 5% to 70%. So there is a drastic there is a let's say a huge range of the probability within that small PG range. So here up to the highest level of PG range, let's say 0.4, we cannot confirm it performs within the life safety. Okay, so but in the lower PG range, depending on the regions, so we can see this is about 40-50%. So we can see in this range it can perform satisfactorily. But if the material quality is improved, then this curve is here for the good quality material, and this performs this performs well within for the given hazard range. Okay, so the probability of being in the life safety is only about 5%. But if the material quality is poor, then it is already from 55% to almost 100% probability. So that is we can say that is unsafe. So this is how we can analyze with the different material qualities, the before and after strengthening, and compare against our seismic hazard, whether the intended retrofitting can provide the required safety level for the buildings. These are some of the key points. So that's just a summary of what we discussed. So the assessment, both qualitative and quantitative, to identify the deficiencies in the existing condition is very important for designing any strengthening. Retrofitting needs to be justified by several factors, such as remaining life of building. If the building is expected to have 5 more years of its life, then there is no point in retrofitting. We also need to identify how much cost the retrofitting incurs, how much historical or cultural values the building has, and also on the how much disturbance to our functionality is caused by the retrofit work. The retrofit design should be verified by detailed vulnerability assessment, as I showed you in the previous slides. The retrofit material and elements should be compatible and integrate well to the existing structure, as you also saw in Juan Carlos' presentations. Care should be taken to keep the disturbance to the original integrity of the building to minimal level. Skilled and trained manpower is necessary for retrofitting work, because this is not new construction, but this needs more careful attention while working, not to be too invasive to the existing structure. And if there is budget constraints, then we can also implement incremental retrofitting, where we install the retrofit elements at stages. For example, here you can install the 3 elements at one phase, and in the next year or 6 months you can then install one by one. But it also depends on other priorities. For example, if you apply incremental retrofitting, then you might be disturbing the functionality time to time. But if you do all at once, then you have only one time disturbance to the functionality of the building. And that is all of my presentation. Thank you very much for your kind attention. Any questions, please, in the chat box, or open your mic.
Thank you very much, Rohit, for this very interesting presentation of how to compute the improvement determined by the retrofitting, and how to consider that in through the fragility function in probabilistic terms, and therefore in the reduction of risk that is associated with that particular retrofitting typology. Is there any questions from the audience, please? Or comments, or if not, we can maybe go on to a short break of 3 minutes, and then we will resume with the next lectures. Thank you.
However, they represent the bonding, the shape or size of these stones, the quality of mortar is very, very similar. So these are not assumed, but obtained from actual tests.
Okay, any further feedback from Arturos? Otherwise, we will go on to the next presentation from Dr. Rafael Fernandez, which is about concrete frame structures retrofitting. Please, Rafael.
Thank you very much, Dina. Thank you, Rohit, also for your previous presentation. As we have seen now in this course until now, we have been focusing on reinforced masonry buildings. So we are now going to change a little bit, and we are going to talk of RC buildings. So yesterday we saw different types of damages and how these buildings have behaved in previous earthquakes. So based on that, we can identify the deficiencies, and based on those deficiencies, then we can assess the buildings and retrofit the buildings so they will have a better behavior. Just to recall a little bit, we talk of this document, the FEMA 647, in which we have different type of deficiencies. The first one is global strength, when the building does not resist a particular level of force that is applied to it. We also discuss a little bit about global stiffness problems, where the structural relation between the displacement and the force that is applied is not enough. But there are so many other problems, such as configuration. Some buildings with vertical or horizontal configuration that induce some type of torsional movements can then make the structure more vulnerable than it really is. In addition to that, there are some additional problems, such as load paths. For example, buildings that have located some type of machines or some type of specific loads in some stories that make the behavior of the structure not as expected. And there are others, like inadequate component detailing. This was seen in many previous earthquakes, problems with the detailing of the rivers, and diaphragm deficiencies and foundation deficiencies. We also saw those buildings that were tilted because of problems with the foundation. In those cases, and for each one of these deficiencies, there should be a rehabilitation measure, and the FEMA 647 presents a correlation between them, and we are going to see throughout this presentation that relation precisely. In relation to the rehabilitation measures, there are 5 main types or categories of rehabilitation measure. The first one is adding elements to existing building. So you, for example, have your building as it is with some particular vulnerability, then you can add some shear walls to the building, and with that you will enhance the structural performance of the general building. You will have a better behavior in terms of strength and stiffness. Other possibilities to enhance the performance of existing elements, for example, not to add any shear wall or steel bracing, but to make the columns to give them a better characteristics. So with this can be done through confining existing elements, and this confinement can be done with a concrete confinement, steel confinement, or even FRP confinement, as we're going to see in a moment. Other possibilities to improve connections between components. You can also reduce the demand. If you isolate the base of the building, you will reduce the demand of and the forces and the stresses that will feel each one of the members. And in that sense, you can improve also the behavior of the entire building. And finally, removing selected components. So for example, if you have an infill that is generating a shear, a short column shear failure, then if you remove that infill, or if you isolate that infill at least, then you will have a better behavior. Also, you can remove some floors, for example, reduce the load of the floors, and with that you can also improve the behavior. So we're going to see by each one of the different structural systems that we discussed yesterday. So in the first part of this presentation are the reinforced concrete bare frames. In the FEMA 647 they are called C1, while in the glossy approach they are called RC1. These buildings are the ones that are composed that include beams and columns as the main structural system, and it's the system that will withstand all the gravitational but also all the lateral forces. In this case, the partition will not interact with these elements. So in this case, we can see this type of table in the FEMA 647, in which you will have in here the category, and for each one of the categories, a particular deficiency is specified, and for each one of the 5 rehabilitation techniques, a suggestion is included. In some cases, like in here, you will have no recommendation, because if the problem is a deficiency related to the global strength, improving connections between elements will not improve the strength, the general strength of your building. In that sense, if we think about that problem of global strength and global stiffness, one of the most common approaches is to add new elements, and we are going to see in the next presentation a particular case in which this was done and how it behaved after the Turkey earthquake. But in this case, for stiffness and strength, we can include, for example, shear walls, concrete or masonry shear walls. We can include steel brace frames, or we can include any other type of stiffening material that will enhance the lateral behavior of the building. In that sense, one of the most common approaches of this adding new elements approach is to add shear walls. This can be implemented in spans, as you can see in this picture, or you can implement it as buttresses in the exterior of the building. This implementation, of course, is easier in terms of you will not disrupt the functioning of the building, but in some cases it's better to add them between spans, so the behavior will be better. This approach has, of course, its advantages and its disadvantages. Usually it's a little bit difficult to ensure the attachment between the new steels and the existing concrete. Drilling these holes and including some epoxy material is a time-consuming task, but it requires only some traditional building skills. People usually know how to work with reinforced concrete, so it is possible to do even in rural areas. One of the main problems of this is that it has a very high architectural impact. So if you, for example, add a shear wall, a concrete shear wall in one of these spans, then you will have practically a new building, because usually you don't need only to do this in this span, but also in some others, and you will affect the facade, and that's not expected or is not wanted in, for example, heritage buildings. Here you can see some process, some pictures of the process. You can see some connections with the new steels and existing steels over here, but you can also see from the pictures that this is a process that is not a trivial process. It takes time. These type of connections and holes are very complicated to do in field, but they certainly can be done. In here you can see a school building in El Salvador. This was a picture taken in 2018. And in here you can see in this span the addition of a shear wall for retrofitting of this building. Other possibility is to include steel bracing. These frames are relatively easy to install. You only need to weld all the frame and then install it directly. So it has a relatively fast construction, and the architectural impact is not that high because you can still maintain your windows and some openings over here behind the steel brace. The main problem of this is that some skills related to steel and welding are needed. So these type of skills are usually not found all across the countries. For example, maybe in an urban scenario, it will be possible, but if you are far away in a school, in a rural school, in a developing country, there will be more complications in this installation. Here there are two videos of a test that was done in Universidad Católica del Perú in 2016. They wanted to see the formation of the short column over here. So you can see in this building, they try to do a school building. This is a classroom. In here you have the restriction of the infills in both sides. So all the deformations will concentrate in this short part, and therefore the shear stresses will be higher than the capacity of the elements, and you will have that type of damages. And the other option was to retrofit the structure. So you can see in here a brace, a steel brace that was included in the building, and this helped with the behavior. You can see now that the short column is not forming over here. You have in this particular test one steel brace in this axis and one in the posterior one. So the behavior of the building for the same ground motion is much better. These are some pictures that we took of this retrofitting of a building in Universidad de los Andes in Bogota. And they welded all the frame infield just besides the spans. And with this, then they install it as you can see in here over these walls. The architectural impact was relatively low. You can see in here that from inside you can still see the bracing, but it will not affect in any case the ventilation that is over here and any of the windows and the illumination. And here there's a table that was just temporarily installed to protect this part, but this was taken down when the retrofitting finished. So you can see in here the process of installation. They just tilt it up and install it directly. Other possibility when there's problems not with the strength of the steel or the stiffness of the complete building, but with particular elements is the component detailing. So you can have problems related to a strong column and weak beam, or problems associated with inadequate shear strength in the columns, which is the most important, but also you can have that type of problems in the beams, or problems with the splices, that the length is not enough. And in those cases, the solution is not to add new elements, because you will still have a very weak existing element. So the solution will be the next rehabilitation technique, that is enhance existing elements. And that can be through the jacketing of existing elements. This could be done with concrete, with steel, or with some fiber polymer that can be used as we're going to see in a moment. So one of the main problems is compression problems. As you know, in confined concrete, as you can see in this picture, will behave much purely in comparison with confined concrete. You can see that the strength is lower, but also the ductility is lower in comparison to the confined concrete, as you can see. So you can add ductility with confining existing elements. So this confinement can be done through concrete, steel, or FRP, as I just mentioned. Particular for the concrete jackets, you will need to first roughen the existing structure. Then you need to install the new steel over here, all the confining loops, hoops, and the vertical bars as well. And you need also to drill some dowels over here to connect the existing element with the new one. So one of the most critical problems of this type of retrofitting is that you will have a larger cross section than the existing one. So you will have an architectural impact inside your building. There are some complications. You need, for example, to ensure a 135-degree hook over here. So for that, you will need to increase a lot the section, but this can be done. It is very important that if the type of retrofitting is aimed to increase the axial capacity, but not the flexural capacity, then it's important to leave this type of gaps over here so the plastic hinge can develop in the element that you are analyzing, that you're trying to retrofit. Other possibility that will not affect that much in terms of area of the element is a steel jacketing. In here you will include some steel plates with, again, some drill dowels over here to connect this new element with the existing one. The main problem of this is that this type of retrofitting is very heavy, as you can imagine. All this steel covering all the columns in your building will add a lot of mass to the structure, and that will they may generate an additional deficiency. So this needs to be considered when the retrofitting is designed. Also, you will need some specific capacities to weld this type of plates and to ensure that they will work as a confined element. Other possibility is to include these FRP bands. In this case, this type of bands work very good in circular columns because you will have the confinement of all the area of the building, of the column or element that you are analyzing. When you have rectangular columns, the problem is a little bit more difficult. You first need to round the existing corners, and you need to ensure a ratio of these columns that is not greater than 1.5, because if it is, then you will have some parts that will not be confined after the implementation of the FRP. The main advantage of this type of retrofitting, of course, is that if you include this, you will not have any impact in the architectural part, because you will not increase that much the section, but also you will not add a lot of weight. However, this material is not perfect. The behavior of the FRP is usually an elastic behavior and a brittle with a brittle failure. So there's no ductility in this type of materials, even though the stiffness is usually higher or at least similar to steel, you will have some problems in relation to ductility, even though you can have a lot of this additional strength in this type of elements. But the important thing in here is to consider the type of behavior of this material. You can do the FRP jacketing and any type of jacketing, but the advantage of the FRP is that you can also install in different sections of the column, depending if you want, for example, to confine the concrete to a axial capacity, or if you want to retrofit only because a problem of bar splice encasement, and in that case you will only add the FRP jacketing in the particular part of the bar splice, or you can improve all the columns in different regions of the column. You can install it from the top to the end, and you will have a particular behavior. You can even leave some areas to let the plastic hinge develop exactly where you want it to be developed. So what we saw until now is the bare frames. Now let's see what happens with the masonry infills. In the FEMA 647, they are called C3. while in the glossy approach, they are considered as RC2 and RC3. In this case, as we saw also yesterday with the different building with the damages in buildings in previous earthquakes, one of the most critical type of damages in this building is the failure of the masonry infill walls, and in particular the out-of-plane failure of these buildings that generate an additional threat to the human life. On the other side, the in-plane behavior will affect the structure and can generate problems in the existing elements, for example, a problem of short column. So the first thing is to understand very well how the masonry infill affect the performance. The first thing is that you will have an increase in lateral stiffness. So you can see in this pushover curve with the continuous lines, the behavior of buildings with masonry infills, and with the dotted line, the behavior without considering the infills. So in the first part, you will have an increase in the lateral stiffness, but also an increase in strength. But after some point, when these infills start to fail, you will have a decrease in the capacity in terms of strength, and you will have a damaged frame. So the most important problem to be considered of this type of building is that you will have a reduction of the ductility in the structure. So this will generate some kind of brittle behavior that is not wanted in this type of buildings, as we saw with the capacity design approach. In that sense, it's very important to understand the failure modes, the in-plane failure modes and the out-of-plane failure modes. We have different type of corner crushing, for example. We have central crushing over here. We can have this type of shear friction failure or some diagonal tension failure. And out of plane, it will depend on how is the connection between the frame and the wall. Rohit explained a bit of this. So we already understand how is this behavior. And in particular, when we analyze this type of walls inside a frame, as you can see here, what will happen with this frame is that you will have a behavior when you apply some lateral force, like this was a compressive strut. If you have any openings, the strut will behave something like this. But the most important problem of these struts is that an additional load that is not considered will be applied to the column over here. So you will have a different shear behavior and a different bending moment behavior. So your column probably will not be designed to withstand this type of shear behavior. Also, if these infills are located in different stories, you will have then an additional negative effect that this will cause some concentration of inelastic deformation in the ones that you don't have any infill. So, for example, the type of deformation that you expect in this frame without any infill is something like this. But when you add an infill over here, which is pretty common, to leave the first floor, for example, as a garage or as any commercial activity, then all the deformation will be happening only in this first story, and you will have the first story, the soft story mechanism that we saw previously in the Turkey earthquake. Again, we can go to the FEMA 647 tables in which they relate the deficiencies with the rehabilitation techniques. And we can see here that if the problem is global strength, then we can do different alternatives, such as adding new elements or enhancing existing elements. We already saw how adding new elements can be done through the implementation of steel braces or shear walls, and how enhancing existing elements can be done through the jacketing of columns and structural members. But since in here we are talking about infill, we can also enhance the performance of the infill to avoid, for example, out-of-plane failure and to generate a better behavior in plane. So this can be with this type of wire mesh that will contain the wall, so it will not fail out of plane, and an additional retrofitting or implementation or intervention is to isolate the element over here, as you can see. So they will not interact with the RC frame, but it will not fail out of plane thanks to the wire mesh. Here there are other rehabilitation techniques when the problem are load pads and component detailing, and you can see that there are possible different ways of implementing this type of retrofitting. We saw this type of mesh, but that can be also done with FRP or with shotcrete or with ferrocement or any other type of material that will stick to the walls. Each of these materials have, of course, a lot of advantages and disadvantages. FRP, for example, have a very high strength and stiffness and a very low weight, but it has a lot of problems with anchorage. It does not dissipate any type of energy, and the brittle mode of failure may be also a problem, while the shotcrete can dissipate some energy, and the shear stresses can also be transferred to these new elements. But on the other side, it will add a lot of mass and maybe also impact the aesthetics of the building. So all of these advantages and disadvantages should be considered during this process. One thing that is very interesting of this type of retrofitting is the retrofitting of joints. So this is usually a problem because it is very difficult to retrofit them, but these elements are very important in a building. So you can see that in some cases you can cut the masonry over here, as you can see, and install an FRP jacketing in the elements. But this, of course, is very complicated to do, even though it is possible. Finally, in the last part of this presentation, there is the shear walls. They are called in the FEMA 647 C2B or C2F, while in the glossy approach, they are called RC4. As you may remember from the previous session, these are elements or buildings with vertical elements as shear walls that can or cannot have vertical forces, but all the lateral stiffness will be sustained by this element. So these are used a lot in high-rise buildings. You can see these buildings in Chile that were damaged after the 2010 earthquake. You can see this type of damages of buckling of the rebar, mainly in the end and the beginning of the wall. You can see that type of failure across all the city of Santiago. And the main problem is that the deficiency of this element is that people build them with an adequate wall thickness and only one coating of reinforcement, as you can see in here. So in this case, this is not ideal because you will not have any type of confined concrete over here. So all the behavior and the characteristics of your concrete will be of unconfined concrete. And as we saw in previous slides, this is very poor in terms of strength and ductility. So after that, for the retrofitting of this type of shear walls, you can also go to the FEMA 647 and see the different suggestions and recommendations. But what is most important to understand is that the damages will concentrate in this part of the walls. So therefore, one of the best retrofittings and even one philosophy of design of newly built buildings with this type of walls is to add these elements such as a column at the ends of the wall, so they can withstand the compressive and the tension strength when a lateral element comes in, a lateral force comes, such as an earthquake. The walls also can be retrofitted with some jacketing, with some FRP jacketing, as we already saw in previous slides. So you can see in here some example of this, in which all the wall has been covered with this. As you may recall, this is not effective for axial compression, but you can add some shear strength, and also you will help the behavior of in terms of flexion of this well. Finally, just a brief example. If we have an original building such as this with short column and a low lateral resistance of the moment resistant frames, there are many possible retrofittings, as you can see here: steel bracing, concrete walls, or concrete buttresses. In particular, since in here we are talking of a school building, time of implementation is very important. So in this case, one can select steel bracing as the alternative. You can see the pushover curve of the original and the retrofitted structure, when the original have a relatively low strength and a very low ductility, while the retrofitted building will have much more strength and a lot of more ductility. You can also see the fragility functions. You can see the original construction with a very high fragility functions over here, but then the retrofitted one, you can move all those fragility functions for different damage states. And you can also see that in the vulnerability function. As you can see here, a vulnerability function with a big vulnerability, while you can reduce that in the retrofitted one. For example, for 1G, you will expect less than 5% of damage in the retrofitted one, while for 1G, you will expect almost 70% of damage in the original structure. So just to finish this presentation, besides the technical issues of rehabilitation, there are also some non-technical issues that should be considered. So these usually determine which type of retrofitting you need to implement. The first one usually is the cost. The second is the seismic performance. What type of risk is acceptable? For example, if we are talking of a residential building, is different than if we are talking on a hospital. So we need to see what is the acceptable level of hazard. Then we have some short-term disruption to the occupants, the long-term functionality of the building, and also aesthetics in terms of historic preservation. So these are all the considerations that needs to be considered when you're planning a retrofitting. It's not just choosing one of the ones that we saw previously, but also to consider all the impact of this decision, all the impact that this will have on your project. Thank you very much. This was the RC part. Now I will give the word to...
Thank you very much, Rafa.
Thank you.
I don't know if there is any quick questions, or considering we are 10 minutes from 4 o'clock, maybe we can pass directly to the presentation by Asana, and then we can have some discussion at the end.
That's great. Thank you, Dina.
Thank you very much.
Thank you, Dina. Thank you, Rafa. Let me share the screen. I hope you can see my screen.
Yes, we can. Thank you.
Okay, thank you. So I think we have already had a very good overview of all the possible different techniques of retrofitting RC structures in the last presentation. This is a specific case of a residential building block from Antakya, Turkey. As we're all well aware by now about the two earthquakes that happened in February 2023, the first one with a 7.8 magnitude to the west of Gaziantep, and the second one following just 9 hours later further north. We are talking about Antakya, which is in Hatay province, which I will come a bit more detail a bit later. As we have seen in several reports and reportings by now, that the region that is exposed is highly complicated, a complex tectonic system, which is a combination or a joint of 3 different plates, boundaries coming to having a very complicated mechanism of tectonics happening. This particular building was assessed during a field mission to the earthquake affected areas by EFIT, This was as a hybrid mission led by professors from UK and several people joining from Turkey and other countries, contributing to different areas of this earthquake, such as the seismotectonics, geotechnical structures and infrastructure aspects of the earthquake. We visited the area of Antakya on second day, where we are going to see this particular building. So if we look a bit more in detail to the Antakya city, this is one of the most severely affected areas in this earthquake, with more than 3,000 buildings collapsing and several others to be demolished, more than 20,000 casualties, and several of these buildings being built before the modern seismic codes in place. They were having deficiencies for the kind of earthquake that occurred. Even if you see the PGA that was recorded, it is also in areas such as Antakya, it's higher than the highest seismic zone designation, such as 0.4 G, which is the cause of the heavy destruction that is experienced. And beyond that, another consideration is that this is a very densely populated area in a soil that is in a soft soil that, by the side of the river, which also would have led to the amplification of ground motions. So in that city where a lot of destruction happened, there was one building that came out to be still standing, and as a very good example of a good performance in this earthquake. And this has been now quoted as an example and being carried to other cities for their retrofit of deficient structures. And we are talking about this particular building, Antakya Municipality Residential Block A2, which is on the left of this figure. This was part of a complex with 3 blocks. You can still see the 2 blocks that are standing. There was a third one in this empty space, which had to be completely demolished and taken away because it did not survive the earthquake. The building on the left, the A2 block, all of them were built about 50 years ago. They were basement plus 9 floor buildings with about 400 meters square in each floor area. This particular building A2 was retrofitted in 2008-9 as a very specific project by the Middle East Technical University and Istanbul Technical University, which took up this project of assessment of the existing building, its deficiencies, and then designing retrofit using CFRP and RC shear walls. And looking at this process, from the site, we were told that the residents in the other block, the A1 block, they were also interested in strengthening their building, and this was partially retrofitted. This was retrofitted only in the ground floor using only the CFRP technique. So this also survived the earthquake. However, it was subjected to much severe damage than the A2 block. And the A3 block was nowhere to be seen by the time we visited the site in March 2023. So we will look a bit more into the A2 block and see the kind of retrofit that was implemented, and a bit more information on this building from the study carried out at METU. So the initial assessment of A2 revealed through some material testing and some analytical studies on simplified models suggested that it was deficient for the most modern seismic codes, the Turkish earthquake code of 2007, through a demand to capacity assessment at member level for each RC column and beam, and also through a global performance evaluation by counting all the failing members. So since it was built in 1974, 75, the reinforcement used was plain bars, and the strength of concrete was also quite low. So they designed retrofitting using two techniques. So it's a hybrid retrofit using external RC shear walls and CFRP on masonry infills and internal columns. So the first approach of CFRP, as we have seen in the previous presentation, this is to augment the infill panel, the compression and tensile capacity of the infill panels. So as we saw, the masonry infills in RC frames, they act as a diagonal strut under the lateral load. The added CFRP retrofit, they are intended to act as the tension ties. So together they can have the intended effect of under a bidirectional force. So overall, it is expected to reduce the interstory deformations while improving the load carrying capacity and also improving the lateral stiffness. So this was the kind of application that was designed. They would have the strips in the both the diagonal directions, and they would have anchorage to the RC beams and columns using CFRP anchorage. And they would also have cross wall connections. So with this, this is referring to a laboratory study using CFRPs. There has been a lot of studies on the effect and the improvement that is obtainable by the CFRP. Just as an example, I'm quoting this study and to observe how they behave under lateral action. So this study, for example, was shown to have shown to improve the capacity of unretrofitted walls, as you can see from the purple curve to these red and green and blue curves. And the variation among these curves are basically the material properties of the RC and masonry that is in the frame. So in every case, we can see that there is substantial improvement in their load-bearing capacity, and it further reduces the lateral deformation of the frame. So it is also, in addition to the tensile capacity improvement, it also improves the compression capacity, because it keeps the masonry intact while the action, but again, at the same time, while this is okay, the CFRP is found to buckle under the compression load, and the subsequent tension cycle would snap the CFRP. As mentioned in the previous presentation, the brittle failure mode of CFRP is one of the shortcomings of this technique. But however, even with failure of a few fibers or strips, CFRP was still able to continue the load transfer until the very last failure, which occurred at very high deformation ranges, such as 1% drift ratios. So it is an effective and very less invasive retrofitting technique, because it doesn't always require people to be removed for a long period of time. So in this particular building, the A2 block, this was applied on the infill walls within the RC frames, as I mentioned. And also they found that several columns in the basement was corroded, and these columns had to be also retrofitted, and then they were given a coating of CFRP in the columns. And in addition to the CFRP, the second technique applied was additional shear walls, which were external to the building and attached to the existing RC frames, as you can see through these anchor rods and through this technique of shear walls. So these were designed in a combined manner, such that combining these two techniques, both these CFRP retrofit on the masonry infills and the shear walls, they would together provide balanced strengthening in both X and Y directions. So this was then implemented inside some some photos during the construction stage, and this was after the earthquake. So as you can see, the building is very much standing, and people were able to evacuate and safely from the building. So the retrofit was intended for the life safety performance level of the expected earthquake at the location, which it was able to perform. And as you can see in these figures, these additional shear walls are still very visible on the exterior of these buildings. And you can see this building, other components such as unretrofitted masonry infills have undergone damage still. Because this was also studied analytically, it was able to see that the unretrofitted buildings, which had a heavy deformation in the ground floor, was able to restrain the deformation within the code limits of TEC 2007 through this retrofit technique. And the capacity curves as obtained from the original and the retrofitted cases suggest the improvement in capacity up to 3 times, 3-folds. This is about this particular building, and if you are interested in knowing more about the mission and other buildings and other aspects that we have looked into, you can see the mission lecture here. And thank you for your attention. And this particular study is also part of this publications here, so you can have a look if you're interested. Thank you for your attention. If you have any questions, I will be happy to take.
Thank you very much, Asana, for a swift and very interesting presentation on a real case, which has clearly been tested well beyond the level of design that was meant for. Are there questions? Everything was so clear? Or there is too much to digest? So as we have already gone a little bit beyond the time, and we will not keep you any longer, but please feed us back with comments, opinions, what you would like us to broadcast next, whether you have a lecture or some ideas in mind of people that can be included in these activities, please, and that can present themselves, either you or your colleagues, please let us know. Rafael is sharing website.
Yes, Dina, this is a questionnaire. If you, before leaving, can click and fill it, will be very helpful for us just to see how we can improve future courses. Thank you.
Yes, so this is a very quick survey. It takes 5 minutes, 5 questions, or you can write for hours on end if you want, but please let us, we are really looking forward to your feedback. So there is a question. Thank you very much. In which software do you model the retrofitted structure? I think structures. I think this is for both maybe Rafa and Rohit. Can you expand a little bit on that?
Yes, Dina, if you want, I can start. In particular, for RC buildings, there are many softwares that can be used. One of the most common one that is used for design is Aptos Mill as well. In this software, you can also develop pushover for the original and retrofitted condition, but has some limitation. If you are more interested in doing something academic and more technically advanced, then OpenSys would be a much useful software.
So yes, so we did indeed do a course on an initial sort of course for dummy on OpenSys last year, about this time, a bit later in May. if there is interest in the audience, we can perhaps organize instead a course on SAP or other software. You can also use a Seismostruct. The issue is really what, OpenSeas is clearly open source, or ETADS for that matter. OpenSeas is open source, but it requires more knowledge of programming, while the other one are commercial packages. So it will depend, they cost some money to use. It depends whether you have access or not to them. But again, this could be, for instance, some feedback that you can send us if you are interested in that aspect of the procedures of determining capacity curves. We can certainly do a crash course on SAP or ETADS to bring you to speed on that aspect. There is a question here: if the wall face due to foundation settlement, then how to repair it? Who wants to answer that?
I can give a first
Yes.
answer, and then you can complement, Dina. Well, the foundation settlement and in general failure of foundation is one of the most critical problems with existing buildings, because it's very difficult to repair. If the problem is about settlement, but settlement of the entire building, then you can, for example, add some additional type of deep foundation with some special machinery, but to try to stabilize the building. When the problem are differential settlement in the building, then you will have an additional problem, because you need then to try to bring it and delete any attempt of the building. So it is very expensive, even though it's possible. Very expensive, and it's very difficult to do. So I think that it can be repaired if the settlement is small, and if it's in similar settlement in all the building. If it's differential, it's much more complicated.
Yes, I think that, and also it depends whether the settlements is a co-cause of the earthquake, or it's a pre-cause of the earthquake. So if the settlement was already there and there is pre-damage, then of course the building should be repaired, especially if it's a masonry building. This will show up very clearly in diagonal cracks, for instance, or vertical cracks. In the masonry, there are various methods of repairing it. We can provide some references, but basically it's a matter, very often it's a matter, first of all, to fixing the foundation, and then to repatch the masonry with what we call in Italian cuci e scuci, which is basically removing the bricks around the crack and repositioning the bricks with new mortar, competent mortar, and enforced, so that is resolved very often. And then you just re-establish the flow paths of the gravitational loads down to the foundation, and the problem is solved. If instead it's a cause of the earthquake, then again, depends very much on, you might need to underpin the foundation, you might need to consider the quality of the soil. So for instance, in Turkey, we have seen this both in the earthquake in 1999 and in the earthquake, in the recent earthquake. Building have actually sunk almost horizontally into the ground, because the soil underneath is extremely weak. It's very sandy soil, although not necessarily associated with liquefaction. So the water table might not be so high, but still the soil is quite weak and uncohesive, and therefore this can occur. In that case, again, it's an issue, first of all, of soil remediation, but it's also an issue of how then you jack up the building, and very often in this case, the building cannot be rehabilitated or recuperated or salvaged. Yeah. Any other question?
I just wanted to add to that, Dina. There were cases, I think, in the previous earthquake in Turkey, where they had to, even though it was possible to do it, but because of the cost constraints, it was easier to let the building go. And then,
Exactly.
yeah, the ground
Which case it
foundation
depends on the
retrofitting could
value
be.
of the building as well. Can you consider soil structure interaction in the retrofitting procedure? Yes, definitely. In the same way that you can consider soil structure interaction when you are designing a building, you should do an assessment of the building as it is with the soil structure interactions, and then you can model the strengthening either at foundation level or in the upper structures and run the analysis again and see what improvement that has made. Of course, very often when you're doing soil structure interaction, the interest is to move the the natural frequencies of the structures from the amplification that the soils provide. So that it would be one of the things that you would look into. So the type of strengthening or the type of retrofitting that you would look into it would then associate with the idea of shifting the periods to safer and less high and smaller amplification of the incoming action up to the possibility of providing isolation, for instance.
I just wanted
So
to.
there is, yes, sorry, Rui.
That's okay. I just wanted to briefly say about the masonry modeling. I have sent you a link there of the software and approach. It's called applied element modeling, which is a branch of discrete element modeling, because masonry is a discrete assemblage of units bonded by mortar. So the applied element is more efficient in that sense for masonry modeling. You can check the link I have provided to find out more about the method, as well as they have presented some verification examples and so on. This software called Extreme Loading for Structures, it has all the formulations of the applied element method and can be used. The graphical user interface is very similar to SAP 2000 or any other CAD-based software programs.
Yes, one of the limitations of this extreme modeling software is that it's quite expensive, but there are indeed academic and student license that you can request, and the student license, I think, it doesn't allow you for huge model, but you can still at least become familiar with the way of modeling. Yes, and you can even ask for a trial version for a couple of weeks or a month. If you request them, they will provide you a trial license so that you can try yourself. Yes. And similarly for the SAP 2000. So I see that there is some interest in a crash course in SAP 2000. We can definitely try to organize that. It would be good if you respond to our survey so that we can sort of gauge, number of interested people, and because that is a very much hand-on course, and therefore we need to organize ourselves more than just with a simple talk or let's say one-way talk, like in this case. Okay, guys. Any other questions or comments? Then in that case, thank you all very much for attending again, and we will soon let you inform you of the new program that we are developing for the season. Thank you again, and bye-bye, everybody.
Thank you, everyone.
Thank you very much. See you again.
Thank you. Bye-bye.
Thank you.
Bye-bye.